Okay, as promised, I will try to keep up all these project 2 tips until it's due or until I run out of ideas. So this is probably the most common one that people always mess up. So last time we reminded you that when someone accepts the invitation, they can choose their own name for the file name. That's definitely in like the top 3 things that people always miss. This one has a very good case of being top 1. It's these 2 requirements when you call revoke access. And these actually make the project easier, I'd say, by limiting the scope of who's allowed to call revoke and who you are allowed to revoke access from. So the only person who can revoke access from a file is the owner. We are never going to call revoke from the context of any other user. So a user who is not the owner of the file, the person who originally created the file, will never call revoke. We're not going to test it. The behavior is undefined. Your code can do whatever you want. If you want to crash, that's okay. If you want to error, that's okay. We don't care. We're never going to do it in our tests. Okay. And then the second thing that people always mess up, it's kind of related, is that the only people who you can revoke from, if you're choosing to revoke a file and you're the owner, you can only revoke from people who you directly share the file with. And that one will probably make more sense with an example. And furthermore, if you revoke from someone that you shared the file directly with, anybody that they shared the file with should also lose access. Okay, so here's the example that I think makes it crystal clear. So if we imagine that this is the sharing structure, user A created the file, so they're the owner. They shared it with B and C shared it with G, B shared it with D and E, D shared it with F. Who is the only person on this picture who can revoke access from a file? A. Nobody else can revoke access from the file. So if B calls revoke access, undefined. If E calls revoke access, undefined. Who is the only person, or who are the only people that A can call revoke access from? Only B and C. So we will never ever test the case where A calls revoke on D or A calls revoke on F. We're not testing that. Do whatever you want, or don't even worry about it. And it's the case that if A revokes from C, C and G both have to lose access. If A revokes from B, B, D, E, and F all have to lose access. So if you revoke from someone, everybody in that subtree has to lose access. Those are the rules of revoke. Okay, and I would say most of those make the project easier because I don't have to worry about different cases like, oh, what if the non-owner revokes? Or what if the owner revokes from someone who's not a direct child? You don't have to worry about those cases. So it simplifies the project. That's why we really care that you make sure you like take these to heart, because I think they make the project easier in the design phase and also in the coding phase. Okay, and then the final note that I should bring up since we're in the revoking area is that say A calls revoke access on C and G, that means that C and G, or sorry, A calls revoke access on C, that means C and G lose access to the file. Everybody in this subtree, B, D, E, and F, they still have to have access. And crucially, they do not have to re-accept an invitation. So if you call revoke on C and G, everybody else should be able to keep using the file as if nothing happened, which kind of makes sense if you think about a file sharing system in real life. If you revoke access from someone, everybody else should not have to re-accept an invitation to keep using the file. They should be able to continue using the file like nothing happened. So for example, if A calls revoke on C, C and G lose access, B should immediately be able to call load file, store file, or append to file, and it should just work. B does not have to wait to receive another invitation or accept another invitation. B, D, E, and F, they all have to be able to continue using the file as if nothing happened. Okay, because from their perspective, they weren't revoked. They should still have access to the file. They do not need to call accept again. And that is also something that kind of limits the scope of possible solutions and hopefully makes things easier. So that is what I wanted to remind you. People miss it every semester and they always come to us like 3 weeks in the project. Oh, I didn't know only the owner can revoke. Only the owner can revoke. They can only revoke from someone they directly shared the file with. If you revoke from someone you directly shared the file with, everybody in that subtree loses access. Okay, I've said it like 5 different times. So if you watch this lecture, like I think you got it. This example even writes out exactly what I just said. Okay, so everyone good with that? We're not going to mess this up this semester, I hope. Okay, fingers crossed. Okay, anything else you want to know about project 2, revoke access before we get started? Yep.
Example can be revoked.
So can be revoked it's undefined, right? Whether you allow it or not, we don't care. We are never going to test a case where B calls revoke, if that's what you're asking. Yeah, that's a great question. Okay, anything else you want to know about this picture, the graph? Okay. Excellent. So now we have that taken care of. No one's ever going to mess that up again. Surely, fingers crossed. Okay. So last time we left off, I told you about ARP, which is our first lower level networking protocol. Remember that the reason why ARP exists, do I have a slide for this? I don't know. Maybe I do. The reason why ARP exists, maybe I have a summary slide. Okay, let's use this. So the reason why ARP exists is because we have IP addresses, which are used to address computers at layer 3. And we also have MAC addresses, which are used to address computers at layer 2. So every computer has two different ways to refer to it. You can either use the MAC address to refer to like the physical hardware on the computer, or you can use the IP address, which encodes some information about where this computer is in the world. So both of these addresses have different meanings. They're both necessary. And so ARP is the protocol that lets me translate one to the other. So if I know somebody's IP address, but I don't know their MAC address, ARP is the protocol that will translate it for me. And the protocol is simply, if I need to know what the MAC address is, I go to my local network and I shout to everyone in the local network, I broadcast and I say, I really want to know who has the MAC address corresponding to this IP address. I'm intensely curious about this. Can somebody help me? And the goal is that the person with this IP address, if they're in the local network, they will respond to you and say, that's me, that's my IP address, here's my MAC address, now you know. If the person is not in the local network, then the router can respond and say, that person's not here, but here's my IP address and here's my MAC address. If you send the message to me, I can forward it to Bob or whoever the other person is. Okay, so what's the attack? Well, the attack is that if I broadcast this request, the attacker could just reply and lie and say, that's my IP address, here's my MAC address, even though that really wasn't their IP address. So the attacker can lie and return their own malicious IP address. So here's Alice broadcasting the request to everyone. You've seen these slides before. Here's Mallory lying and saying, yeah, that's me, even though it's not. And here's my malicious MAC address or my own MAC address. And if her answer gets there before Bob's answer, then Alice will accept Mallory's answer, cache it. Now, the consequence of this attack is that in the future, if Alice ever wants to send a message to Bob, she looks in our cache and says, well, where's Bob? Well, Bob apparently lives at this MAC address, so I'm going to send a message to Bob, and then the message gets sent to Mallory instead. Okay, so here were the properties of ARP spoofing and why it's a problem, or why it even exists. The one problem that we talked about at the tail end of last time is that Alice has no way of verifying the response. There is no cryptography in this protocol. There's no way to tell whether someone is truly the IP address holder or the person who holds the IP address you requested, or if they're lying about the IP address. You simply have no way of telling. This protocol is just too simple for that. Other problems are that Alice is not expecting two people to respond. If she says, who has the IP address 1.2.3.4, she expects a single response, not like 10 different responses. So she's going to accept the first response. And that means that if the attacker's response shows up first, it will be accepted. And then the second one will just get thrown away, depending on implementation, but usually just ignored, right? Because you don't expect a second one. And if Bob responds first, then, well, now the attacker's response is going to get thrown away. That's called a race condition. Is going to come up over and over again as we see different networking attacks. So sometimes if Alice is expecting one response, then it's really a matter of whose response gets there first. So that's what the race condition is. Some attackers can win the race conditions. Some attackers can't. If you don't win, maybe you have to try a bunch of times. That depends on your threat model. Okay. And so what does ARP spoofing require from the attacker, and what does it allow the attacker to do afterwards? So I think of ARP spoofing as like an upgrade attack. So to do ARP spoofing, you first have to clear the qualifier of being an on-path attacker. You need to be in the same local network because this entire protocol operates at a local network level. Alice broadcasts the question to everyone in the local network, and she gets a response from someone in the local network. So in order for you to carry out this attack, you need to be in the same local network as the person asking the question. So that basically makes you an on-path attacker. You're the person who can read the messages being sent from Alice to everybody. So that's the requirement to execute this attack. The prerequisite is you have to be an on-path attacker. But if you are an on-path attacker and you execute this and you succeed, then you upgrade yourself into a man-in-the-middle attacker who is more powerful. Man in the middle can additionally tamper and drop messages. So why does the upgrade happen? Well, the upgrade happens because after the attack, any message bound for Bob is now going to get sent to Mallory instead. So Mallory can take that message, modify it, drop it, tamper it, and then send whatever the modified message is to Bob. So now she is the man in the middle, and she can tamper with messages however she wants. So you can kind of think of it like an upgrade attack. Mallory used to be an on-path attacker and has to be an on-path attacker to execute this thing. But when she succeeds, she upgrades herself to man in the middle. Okay, that's mostly review from last time. So I got so really cut off at 6:30 about the defenses. So let's talk about those. Okay. So the main defense is that in real life, when you execute this ARP protocol, you're usually not going to broadcast the request to everybody on the local network because that could be too many people. That leaves you too vulnerable to attacks. So in general, this is kind of a very high level overview of a possible defense. Most local networks have something called a switch. And the idea is that the switch is some like central computer, sometimes it's the same computer as the router, or some server sitting on the local network. And the switch is going to maintain its own cache. So instead of you broadcasting the request to everybody every single time, you're instead going to walk up to the switch, ask the switch, hey, do you actually know who Bob is and what their IP and MAC addresses are? And if the switch knows, then you don't have to do any broadcasting at all. And you save yourself an ARP protocol. You maybe save yourself from being attacked using the ARP spoofing attack. So if you walk up to the switch and the switch knows the answer, then you don't have to broadcast. If you walk up to the switch and the switch doesn't know the answer, then the switch has to broadcast anyway. So it doesn't completely stop the ARP spoofing attack, but it makes the broadcast step and the reply step a bit less common so that it's less possible to make the spoofing attack happen. Okay, so you can kind of think of it as if there's this central switch that's maintaining the mapping for everybody, then probably the central server is going to have a larger cache because it's collecting requests from every single person on the local network. So in general, the switch is going to have to broadcast less often. And if you broadcast requests less often, then the attacker has fewer chances to successfully run the spoofing attack. So that's one of the benefits of switches. There's fewer broadcast requests, and we know that the broadcast requests are the things that are vulnerable. It's also more efficient in general. So this one definitely depends on your specific network and how you're building it. But in general, switches are kind of nice because now you don't have to broadcast as many times. So if broadcasting is expensive somehow, maybe you've saved yourself some time. And switches can get a lot more complicated. We are like barely scratching the surface here, but you can even use switches to do something like take a single local network and split it into a bunch of smaller local networks. So even though at a like physical level, everyone is connected up in a single local network, if you feel that the local network is too large, you can use switches to split the local network into smaller local networks, which are called virtual local networks. And they're called virtual because in reality, everyone is connected up, but you use the switch to isolate different parts of the network into their own local networks so that if you broadcast, you're not broadcasting to everybody, you're just broadcasting to one specific isolated section of the local network. So that might be nice if, for example, you're running like a company or something, and you want to have this like top secret local network that's really secure, and you want to have this broader local network that's less secure. Well, maybe you can use switches to do that. So we're just kind of touching the surface here, and it's not something we're going to talk about in detail, but that's the rough picture of ways you can kind of help stop ARP spoofing. None of these are bulletproof defenses, and we'll have to wait until later to see what the bulletproof defenses are, but it's a start. Okay. Finally, there are also some tools out there. So this is like a software level fix where maybe you can like run some software on your computer and you can check if there's anything that's kind of suspicious. For example, if you see 2 responses come back when you made a single request, that might like make you think, oh, something is kind of weird here. And so some tools like ARP Watch are designed to do just that. So they're going to sit on the network, watch the ARP requests go back and forth. And if they see something really suspicious, like, hey, there were 2 answers that came back, or like there's this one computer that keeps answering every single query and it's kind of weird, then maybe the tool can alert you. So those are possible ways to help defend against ARP spoofing, although they're definitely not bulletproof. If you want a real secure defense, you're going to have to come back in a couple weeks. Okay. Final thoughts on ARP. It's the very first networking protocol, the very first attack, the very first defense. Okay. Let's do another one. This one's called Dynamic Host Configuration Protocol. I will never ever test you on what it stands for, but it's called DHCP. So here's what it's for. So the reason why DHCP exists is because when you connect to the network for the very first time, you have to somehow like get yourself set up. So if you go back to the postal analogy, it's like when someone moves in for the first time, they have to get set up. They have to remember things like, oh, this is my address. And here are all the addresses of my neighbors. And here's the address of my nearest post office. So you can imagine when someone moves in for the first time, they have to get themselves situated and start thinking about like, oh, well, my address just changed. Here's my new address. And since I moved into this new place, my new post office is over here. So I have to remember all these things. Here's what it looks like in kind of the computer world. So when you first join a network and connect to the internet, you need a couple things. You need an IP address. So when you first move in, someone needs to tell you what your address is. In the same way that if you first connect to the network, someone needs to tell you what your IP address is, or you have to be assigned an IP address so that other people can send messages to you. You can send messages to other people. So you need an address for yourself, the IP address in particular. So that's something you need. You're also going to need the IP address of a DNS server. We haven't talked about what DNS is, unfortunately. We'll talk about it in a couple of weeks. So for now, you can just imagine the DNS server is some helpful friend who's going to provide some useful service, and we have to know where they are so we can go find them. But what they do is a problem for another day. And finally, we should also know the IP address of the router, sometimes called the gateway. This is the server, the post office, whose job it is to forward messages outside the local network. So if you would like to contact people who are not in your local network, your local apartment building, you need to go to this router so that they can forward messages in the right direction. So these are the three addresses you have to know. But when you first connect, you simply don't know this stuff. You don't have an IP address. You don't know where to find this helpful friend, the DNS server. You don't know where to find the router to send messages to the rest of the world. So DHCP is the protocol that's going to help us learn all this stuff for the first time. Okay, let's see what it looks like. And as I go through it, it's going to smell and feel kind of familiar. So let's do it. Okay, so the first thing we do is when I first move in, I don't know anybody. So the best I can do is I'm just going to broadcast. I don't know anyone. I don't know who to ask. So I'm just going to start shouting to the world and everyone in my local network. I have just moved in. Can anybody please tell me some configurations that I can use? Like tell me where to find the helpful friend, the DNS server. Tell me where to find the router. So you broadcast this request to everybody, and you can receive replies. So different people might be able to offer you information like, here's an IP address you can use, and here's a DNS server you can contact, and here's a router you can talk to. And multiple people might be able to offer. In practice, it's usually just one person that offers, but in theory, multiple people could offer. So maybe there are like 2 DNS servers sitting in the network, or there's like 2 different routers. So maybe there are multiple different configurations that you can choose, even though in general, there's probably just one. And each configuration has to come with an answer to all of the questions. So each configuration has to say, here's the IP address you're using. Here's your helpful friend DNS server you can go talk to. Here's the router you go if you want to send messages to the outside world. So that's the offer itself. And so here you are, you've been courted with all of these like wonderful offers, and you have to pick one. So you're going to broadcast to the world and tell everyone, thanks for all the offers. I'm choosing this one. Maybe you just got one, maybe you got multiple, but either way, you're going to tell the world or tell everyone in your local network, thank you for all the offers. I'm choosing this one. So this way, everyone who has not been chosen can say, oh, okay, you're not using this. Okay, I can save this for somebody else, or offer this request, or offer this like IP address to someone else in the future. So I'm going to discard, if I wasn't chosen, whatever offer I made. And if I was chosen, okay, that's great. I'm going to keep my assignment, like my IP address assignment, the DNS server, router, and I'm going to remember that this offer has been accepted. So here the client is broadcasting to the world and saying which offer was accepted, and everyone acts accordingly. Okay, and then finally, the DHCP server, whoever's making this offer, is going to send an acknowledgement, and we'll see these things over and over again. But this is just like a confirmation email. It's like a receipt that says, okay, like you have chosen to accept my offer. I agree that you have accepted my offer. So we both agree that we're using the same offer and that it's been accepted. So this way, both sides get to agree. It's like a receipt or a confirmation that everything has worked out. Okay, it's 4 steps. Let's look at it in pictures. And again, it should feel kind of familiar from ARP because it kind of is the same thing. Alice comes up, does not know the answer to some question. The question here is different from an ARP. But still, there's some question, which is like, what's my configuration? I don't know. And just like in ARP, when I don't know, I broadcast to the world and say, can anybody please help me? So we broadcast to everyone in the local network, oh, please help. I need a configuration. I just moved in. I just connected. Okay. And well, now she's going to get some responses. So she might get one response. She might get two responses. And each response has to come with all of the answers to her questions. Like, here's an IP address that I can assign to you that you can use from now on. Here's a DNS server you can contact as a helpful friend. Here's a gateway you can contact for the rest of the world. So different servers could offer different answers. She might get multiple offers. She might get one. And either way, whenever she picks her favorite, if she gets multiple or if she just gets one, when she picks the one that she likes, she's going to broadcast to the world and say, thank you everyone for the offers. I'm going to use the one that DHCP server number 1 sent. Everyone else, thank you for playing, but I don't need those. Okay. Great. And finally, DHCP server 1 is going to somehow do some reservation that says, okay, IP X belongs to Alice. Nobody else can use this IP. I can no longer hand out this IP to other people because Alice is currently using it. This is the DNS server she's going to talk to. Here's the gateway router she's going to talk to. And then the DHCP server 1 sends like a receipt or a confirmation or an acknowledgement that says, okay, you've agreed to use this configuration. I agree to give you this configuration. We're all happy and everything is worked out. Okay, so that's the protocol. Again, it feels kind of similar to ARP because it kind of is. And so guess what? The attacks are kind of the same as in ARP. So the vulnerabilities are also the same. What was the problem that made ARP so vulnerable? Well, one of the problems was that in ARP, when you screamed and shouted and asked who has the IP address, MAC address mapping, and you got an answer, you had no way of telling whether the answer was correct. There was no cryptography. There was no way to verify who was sending you the response. So in the same vein, when you use DHCP and you like ask the world who can offer me a configuration, you have no idea who answers the question. So Alice has no way of verifying who the response came from. Just like in ARP, they have the same problem. And this means that both of them have the same vulnerability, which is that anybody can lie and answer. So just like in ARP, where someone can walk up to you and lie and say, oh, I have this IP address, here's my MAC address, and lie about the answer. In DHCP, someone can also lie and say, oh, here's a configuration just for you. And some of the configuration could be malicious or messed up, and Alice has no choice but to accept it. Okay. And another problem that's very similar from ARP is that in general, Alice cannot be sitting there waiting for lots of people to respond. She can't be so picky and say, I'm going to sit here and wait for 10 people to respond before I choose my favorite. What if 10 people don't respond? What if only one person is ever going to respond? So in general, Alice is going to just accept whoever comes first. This is implementation dependent. Like if you really wanted a DHCP protocol that accepts the second answer, I guess you could. But in general, since we really only expect one response, we're not going to sit there and be like, oh, but what if there's a second one? You don't know. So as soon as you get one, you're usually just going to accept it. And that introduces another race condition, which is that if the attacker's malicious answer shows up first, Alice is probably going to accept it first, because why would she sit there waiting for the second one to show up? This one is, kind of implementation dependent. If you want to implement the HCP differently, you could, but that's what we have on the slide. Okay, so what can you do with DHCP? So just like before, we think about what is the prerequisite to making this attack happen? Well, again, you have to be in the same local network to execute this attack. For the same reason as in ARP, this is an attack happening at the local network layer. It's only happening within a local network. You broadcast and shout the question to the local network. You get configurations from the local network. So in order to execute this attack, Mallory needs to be in the same local network, just like before. And just like before, if you succeed at this attack, you upgrade yourself from an on-path attacker who's in the local network reading messages, and you upgrade yourself into a man-in-the-middle attacker who is now able to tamper with messages as well. Okay, so how is the upgrade going to happen here? Well, remember, Mallory can lie about any of the configurations. So imagine if instead of honestly saying, that's where the post office is, Mallory says, I'm the post office, come talk to me. Well, now what's going to happen is anytime Alice wants to send a message to the rest of the world, where's she going to send it? She's not going to go to the real post office because she has been tricked to thinking Mallory is the post office. So any messages sent to the rest of the world end up going to Mallory instead. And now Mallory can take the message, modify it, and then send it forward to its destination. So one possible way to use the HTTP to lie about something that gives you the man-in-the-middle capability is you can lie about the gateway router. Instead of saying, that's where the post office is, so messages for the rest of the world should go there, you can lie and say, I'm the post office. Messages to the rest of the world should come to me. And now anytime Alice sends a message, it goes to Mallory first. She can do whatever she wants to it. She can drop it. She can modify it. She can add on her own messages, and then she can send it forward to the destination. That makes her a man in the middle. And even though we haven't talked about what the DNS server is, you can imagine that Mallory could also lie about that too. So instead of saying, that's where the helpful friend is who can answer all of your DNS queries, whatever those are, Mallory could claim that she is the helpful friend and any DNS query should go to Mallory instead. And that could be bad if we're relying on this helpful friend for some sort of like information that we care about. I promise you we'll talk about it when DNS comes up, but you can imagine that Mallory lying about this is also bad news. Okay, so this slide hopefully should feel very similar to the ARP slide. Like a lot of the words are simply copy pasted because the vulnerabilities that unlock both of these attacks are very similar, and the prerequisite to the attack and how the attack upgrades you to be a man in the middle, they're all basically the same. Okay, so here's a slide that like hammers home the idea that they are the same. Both of them have the same key vulnerabilities, which is that the attacker can lie about the answer, that's spoofing. And in both cases, there's some race condition, which is that the attacker needs to make sure their answer gets there first. Both of the vulnerabilities suffer from these attacks because they are broadcast protocols where you ask everybody, including the attacker. And in both cases, there's no way to trust whether the response that comes back is legitimate or not. These protocols are just too low level and too simple for that. Okay. So how do you stop the HCP? Well, it turns out here, I don't even have an answer for you like the switches. I can only say it's hard. And the reason why it's so hard is because when you first join the network, like when you first move in, it's hard to trust anybody. It's like when you move into a new apartment complex for the first time, you don't know who any of your neighbors are. There's no one there who you can really trust, especially if you're being very paranoid. So instead, we're going to have to rely on defenses in higher layers, and we're going to have to punt this problem to a couple of weeks from now. And later, we'll see a defense or a protocol that introduces cryptography that's going to stop all of this stuff. But that's going to be a problem for later. So for now, all I have to do is say, like, stay tuned. There will be protocols later that introduce cryptography that help us stop these attacks. But for now, we just have to accept this as a fact of life and hope that a higher layer helps. Okay, I know it's not the most satisfying answer, but it's the best I can offer for now. Okay, anything else you want to know about these first two protocols? They're kind of similar. They serve different purposes, but they have the same vulnerabilities. Anything on Zoom? Nope. Okay. Great. Let's talk about some more low-level protocols. So now we're going to move into like wireless local protocols and how they work. So everyone's heard the term Wi-Fi before. We're not going to talk about the hardware behind it in too much detail, but you can think of Wi-Fi as this protocol that wirelessly connects up all the machines in the local network. So we are using Wi-Fi to connect all of our machines to the Berkeley visitor network or the EduRoam network, depending on which one's working that day. So that's the Wi-Fi protocol. It uses some like physical wireless technology at layer 1 that we're not going to talk about. The important things you have to know about the Wi-Fi network for this class is that each Wi-Fi network has these things associated with it. So each Wi-Fi network has an access point. This is the machine that helps you connect to the network. So it's sitting somewhere in the network. Remember that the network is just a bunch of machines connected together. The access point is some machine who sits there and its entire existence is just to help people connect to the Wi-Fi network. Each Wi-Fi network has a name. So if you've ever gone and tried to like connect to different networks, everyone has a name. The name is called the SSID. You don't have to know what it stands for, but that's a fancy way of saying every Wi-Fi network has a publicly identifiable name. And every Wi-Fi network, at least the secure ones, they have a password. So you could, I guess, technically have a Wi-Fi network without a password, but in general, Wi-Fi networks, they have a password. You enter the password, that's how you connect. Hopefully sounds kind of familiar. Okay. So how does the thing actually work? So the way it actually works is using a protocol called WPA2, and it helps us secure Wi-Fi networks using cryptography. So we're going to have to design this scheme. I'll kind of walk you through it. We can try to think through the goals together. So what do we need for this protocol to be secure and functional? Well, one thing that is hopefully we can all agree would be good is that if you have the Wi-Fi password, you should be able to join the network. So if you walk up to the access point and you present the correct password, the access point should allow you to join the network. That seems fair. Okay, also, it would be nice if all the messages are encrypted so that if you're not on the Wi-Fi network, you can't look at the wireless messages being sent back and forth and like snoop and see what they say. So it would be nice if all the messages were secured somehow using cryptography. That seems like a nice goal to have. And also, if you don't have the password, I don't know why this says network. Should we change it? Okay. Caught a typo. Let's fix it. So that should say password. Okay. Did it work? It worked. Okay. Sorry about that. Okay. So the final point is that if you don't know the password, you should not be able to join the network, and you should not be able to see what other people are saying over the network. Again, seems pretty reasonable. If I don't know the password, I should not be able to join the network. I should not be able to learn the keys that people are using to encrypt messages. So those are the goals that we want. So now we're going to have to build this thing. Okay. So let's build it. So the way that we're going to build it is we're going to draw this entire handshake. It's going to be a protocol between these two people, and they're going to exchange a bunch of messages in order to make sure that the client is authorized to access the network. And if they are authorized, we're going to give them access to the network by giving them some secret keys that they can use. Okay, so there are two different people in this conversation. There's the client. This is the person who is trying to connect, has the password, and would like to connect to the network. And there's the access point. This is the person who's already on the network, and their entire existence in life is just to sit there waiting for requests and authorize people to connect if they have the password. Okay, let's watch them talk to each other. So the first thing that should happen is the client should walk up to the access point and say, I would like to connect to the network, please. So it's just a request. Client sends to the access point and says, hi, I'm the client. I have the password. I want to connect to the network, please. Is that okay? Okay, great. So at this point, we have to start thinking about design, because one thing we could do is we could just have the client send the password directly, and then the access point could check if it works or not. And we could think, well, does that satisfy all of our design requirements? Well, if the client just goes ahead and sends the password, what if the attacker looks and sees the password being sent? So what if the attacker is reading all these messages and can see the password being sent? Now the attacker knows the password. So we probably shouldn't send the password in plain text over this insecure channel. That would be bad news. So we're going to have to be a little bit more clever. We can't actually send the password, but we still have to somehow allow the client to prove to the access point that the client knows the password. So here's how they're going to do it. It's a little bit more clever and takes a bit more design. So we know the client knows the password, or if this client wants to log in, they have to know the password. The access point is already on the network, so they should know the password too. So both of them are going to run some deterministic algorithm on the password to derive this thing. It's called pre-share key. I'm just going to start calling it blue and start color coding this stuff because there's about to be a lot of acronyms. Okay, so they use the Wi-Fi password, they throw it into some deterministic algorithm like a hash or something, and they get out this blue key, pre-shared key. Okay, what comes next? Now they're going to exchange random nonces. So they're going to each generate a random number and send the random number over the insecure channel to the other person. We'll see why this is useful later. So for now, you're just going to have to trust me that the random nonces are useful, but they are. Okay. And so now we're going to do another derivation. And again, we're going to find some deterministic algorithm, like a hash, a key derivation function from project 2, like pick your favorite. We're going to use some deterministic algorithm, and we're going to take three things and throw them into the soup and get some deterministic output. So the three things that we're going to throw into our deterministic algorithm soup and mix them up, we're going to throw in the pre-shared key, that thing in blue. We're going to throw in the nonces, that thing that I colored in red. And we're going to throw in the MAC addresses of both the client and the access point. So all these values go into the hash or go into this like soup, and out comes a new value. And the new value is going to be called the PTK. I'm going to label it purple. Any guesses why? Well, what happens if you mix blue and red? You have purple. Ah, you see what I did there. Okay, so we take this PSK, the blue thing, we take the nonce, which are these random values that I colored in red. If you mix them together, you get this purple pairwise transport key, or PTK. But the important thing is that both sides are deriving it independently. So it's not the case that one person derives it and sends it to the other. That way an attacker over the channel could see it. They are both deriving this on their own on either side. So notice that the secret keys, the blue one or the purple one, they are not actually getting sent over the channel. Both sides are deriving it by themselves using stuff that they both know. Okay. At this point, it would be nice to check that things have not been tampered with. Like imagine if the attacker tampered with the nonces and now each side has a different key. that would be bad, and I don't want that to happen. So the way that I'm going to check that both sides have derived the same thing and nothing has been tampered with is I'm going to exchange MAC codes from the cryptographic unit, message authentication codes. And this is going to be annoying because, like we said last time, MAC addresses and MACs from the crypto unit, they share the same name. So I'm going to temporarily fix that and hack around it. So I'm going to temporarily rename the message authentication codes from the crypto unit into message integrity codes. So I'm going to call them MICs for the rest of the day. When you see MIC, it's not a new thing. It's just the message authentication codes like HMAC from the cryptography unit. Is it annoying? Yes, it's very annoying. But unfortunately, these two things have the same name. So we just have to hack around it. Okay, so the specifics, I'm going to abstract them away here. If you remember the cryptography unit, we can build specific ways to do this. But you can imagine that both sides generate a MIC, which is the MAC from the crypto unit. They exchange them and check that the messages have not been tampered with. So there's a little more that goes into it, but you can imagine we already know from the crypto unit that MICs have the power to help us check if things have been tampered with. So here we're just leveraging that power to check if things have been tampered with. And if you believe the cryptography unit and the properties of the MIC, then hopefully this feels convincing. If not, you can dig in and think about how they would do this. But for now, we're going to abstract it away. Okay. So at this point, both sides have a key that they share, which is great. And then the final thing that's going to happen now that they both share a key is that the access point is going to encrypt using the PTK, this group key, and send it over to the client. And then the client's going to acknowledge that everything has worked out and that they've received the group key. And the group key I've colored in green because it's separate from all the others. Okay. So I realized I just threw a lot of stuff at you, so we can try to break down and see what all this stuff is actually for. Okay. So to go through it one more time, and then we'll talk about properties. The client walks up to the access point, says, I would like to authenticate. And the access point says, sure, let's do it. So they both derive this blue key from the password independently. They're not sending things to each other. They are simply deriving it by themselves offline. Okay, and then they both exchange random numbers. So each side generates a random number, which I've colored red. And they exchange it over the insecure network. And then they take the PSK, which is in blue. They take the nonces, which are in red, and they take the MAC addresses, and they throw all of those things into a soup and like a hash function or something, and out pops this PTK in purple. Finally, they use MICs to check that nothing has been tampered with. And if you believe the cryptography unit, you don't have to worry about the specifics, but we know that MICs somehow can help us check if things have been tampered with. And if both sets are satisfied that nothing has been tampered with, and the final step is that the access point sends a group key, which everyone in the network is going to share. And they send this encrypted over the network, and the client acknowledges and says, yep, it's been received. Thanks. Okay. Let's see some properties. So what did I achieve here? There's a bunch of words for you. Okay. So what did I achieve here? Did I achieve all of those goals from my 2 slides ago? Well, both sides have a secret key, which is good. So both sides derive the same key. They went from the Wi-Fi password and they threw that into some hash, got the PSK in blue. They took the PSK in blue, the nonsense that they exchanged in red, and the MAC addresses, and they threw all of those things together to get the PTK in purple. And now the PTK can be used to encrypt all future communication. So if you ever want to talk to somebody on this network, you can encrypt the message using the PTK. You can send it to the access point. The access point knows how to decrypt it and then can send it to someone else in the local network. So the PTK can be used to encrypt communication, which is good. One observation that you might make at this point is that the PTK is different for every user. Well, why is that? Because if I run this handshake like 10 different times, I'm going to get different nonces every time. Those are random numbers that I generate, which means that every single time I run this handshake, if I get different nonces, when I run this derivation, I get different PTKs. So if a bunch of different people connect, everyone gets a different PTK, but they're ultimately all talking to the access point anyway, who can forward the messages onwards. So that's okay. But in general, the PTKs that get derived should all be different. Okay. And finally, there was this extra key that got sent. So we were like, there were already so many keys. Why did you throw in yet another one, this green one? Well, the group key, GTK, is useful because sometimes you want to broadcast things. Like we already saw protocols from before that involve broadcast. So sometimes you don't want to just talk to the access point and like ask the access point to forward something to a specific person. You would like to send something to the entire world. or in this case, I guess, the entire local network. So how would you do that? How would you broadcast? You can use the GTK, and everybody who's ever connected gets the same GTK from the access point. So this way, if you broadcast, everyone knows the key to decrypt the message, which is nice. So that's what the GTK is for. You can think of the G as standing for group. So everyone in the group has the same key. This way, if you ever want to broadcast the message to everyone in the group, the local network, use the GTK, everyone gets it. Okay, so those are our properties. We'll see whether it's secure against attackers later, but we've at least achieved our functionality goals, which is that everybody can connect to the network if they have the password. And if they have the password, they receive this set of keys. There's a PTK in purple that they can use to send things to the access point, and the access point can send it to its destination. There's also a GTK, which they can use to broadcast messages to everyone. And that one works because everyone has the same GTK. Okay. It has also just occurred to me that you could maybe argue the P stands for purple and the G stands for green. I don't know. Maybe I'm just a secret genius when I make these slides. Okay. Any other questions that don't involve colors? Okay. Or maybe they do involve colors. I don't know. Okay. So this handshake, it works great. I think it's intuitive. You can think through all the steps and you see these like exchanges happening. So I like it. It's very nice to read, but there is one problem, which is it's kind of slow. So you can imagine that sending messages over the network takes time. If you're using like a wireless protocol, you have to wait for those wireless radio waves to get to the other side. And then they have to think a little bit and then send you an answer. So you can imagine that sending messages back and forth takes time. And if I look at this protocol, I'm sending a lot of things over the network. I'm sending this request, and then I'm sending this nonce, I'm sending this nonce, I'm sending two different mix, I'm sending a GTK and an ACK. Like that's a lot of arrows going back and forth, and each one takes time to send over the network. So this is going to stack up, and it's going to make connecting to a Wi-Fi network kind of slow. I don't like that. So I'm going to make it faster. So this next version of the handshake that you're going to see, it is the exact same handshake. I am not changing any of the semantics. The derivations are exactly the same. They're both sides are going to get a PTK in purple at the very end. The client's going to get a GTK at the very end, the group key that they can use. It is all the same. The only difference is I'm going to slightly shuffle the steps around to try and reduce the amount of messages sent back and forth just to make it faster. So at this point, if you're still feeling shaky about the handshake, this might feel kind of confusing. The important one that really is going to help you get the security properties is this one, the conceptual version. But in real life, since we care about optimization and making things fast, we are going to slightly optimize it. Okay, so let's look at what this would look like. The authentication request, and there's no optimizing that. We have to tell the access point we want to communicate, so that's the same. And they're both going to derive something. Okay, still unchanged. Great. At this point, we're going to send the nonce to the client. So it's called a nonce, I guess, for access point, A for access point, perhaps. Okay, and at this point, we pause. What would have happened in the non-optimized version? In the non-optimized version, the client would have sent its own nonce, and then both sides would have derived something. But if I stop at this point and I look at the client actually has everything they could possibly need to derive the PTK in purple. Why is that? Because the client knows blue, PSK. The client knows red because they have the nonce from the access point and they have their own nonce. They don't need to receive that from someone else. And they know the MAC addresses. So at this point, instead of waiting and like sending another nonce and exchanging a bunch more messages, the client's going to say, well, forget all that. I have all the things that I need. So I'm just going to go ahead and generate my PTK first. So now we're kind of losing the symmetry of this protocol. And the client's going to say, I know all this stuff first. I know my own nonce. I know the other person's nonce because they've sent it to me. I know the PSK because I've derived it. I'm ready to compute the PTK. So I'm going to go first. Sorry, access point. You have to wait till later. I'm going to go first, generate the PTK since I know it. So what good is that? Well, now we can save ourselves a step because now the client is ready to send the MIC because it's so far ahead of the protocol. And so the client can send the MIC and the S nonce together in one step. Remember in the original unoptimized protocol, we had to send these one after the other in two different messages. But now we can send them in one shot because the client knows the S nonce, can send it at this point, and the client already knows the MIC because the client has skipped ahead in the protocol, generated the PTK already. So this saves us an exchange, which is nice. Okay, at this point, we look at the access point. Does the access point know everything? Is it ready to compute the PTK? Well, it sure is, because the access point knows the PSK in blue, it knows the nonces, it knows its own nonce, and it just received the client's nonce, S nonce. So now the access point is ready to do the derivation. It's true the access point had to wait a little bit later, but that's okay. It saved us the back and forth message, which was nice. So at this point, the access point is ready to do its derivation. They still derive the exact same thing. So these two formulas sitting inside these boxes is exactly the same. I haven't changed that at all. The only optimization is that I'm reducing the amount of messages sent back and forth. Okay. And now, again, the access point tries to save itself a message. So it's going to send the MIC, but it's also ready to send the GTK. So it goes ahead and sends both of those in a single shot instead of doing it across two separate messages. And then finally, the client acknowledges. So I took the old message or the old protocol, which had like 6 back and forths, and I've compressed it down to 4, which is an improvement. But overall, if this looks confusing, that's okay. I think it's confusing too, because it's optimized. And in general, when we optimize things, they start to look a little bit less intuitive. So if this looks weird, it's okay. I like looking at the symmetric version where everyone's exchanging things nicely. But once you get the hang of it in real life, this is what people do. They call it the 4-way handshake, because if you ignore the authentication request, which doesn't really have any information or any like cryptographic information, there are 4 things being sent. A nonce, S nonce and the MIC together as one, the MIC and the GTK together as one, and the ACK at the end. That's 4 things. So we cut it down from 6 to 4. We optimized. But it's okay. The ultimate like thing that we're computing is exactly the same. So we haven't changed any of the cryptographic properties of this handshake. We just made it faster, which is good. Okay, that's the optimized version. But again, if you don't like it, the intuitive version is sitting right there for your perusal. In fact, I'm going to go back to the intuitive version when I talk about attacks, just to make things easier. Okay, so what are some different things you can do against this protocol? There are a couple of attacks that we're going to talk about. And so one possible attack is if you are already in the network, so you're someone who knows the password and you've connected to the network, that's the prerequisite for this attack. You know the password, so you can derive the PSK. Well, something you could do is you could pretend to everyone else that you're the access point. So you're lying and telling everyone else, if you want to connect to the network, come talk to me instead of talking to that real access point. So that's called the rogue AP, because you've gone rogue and pretended to be the access point yourself. So instead of talking to the real access point, maybe somehow you can make the client talk to you instead. And we're not going to talk about the specifics of how that actually happens, but you can imagine that if that actually succeeds, well, now the client's going to be talking to you instead. And you know the PSK, so you can honestly follow this entire protocol. The client's not going to know any better. They're going to think you're the access point, and this upgrades you to become a man in the middle, because now anytime the client has a message to send to the rest of the world, they're going to come to you because they think you're the access point, not the real access point. So that's the rogue access point attack. What's the prerequisite to making it happen? The qualification is that you have to be on the network, you have to know the password so that you can execute this handshake as the access point. And what does it do if you succeed? It allows you to become a man in the middle, because the client's going to do this entire handshake with you instead of with the real access point. You're able to do this whole handshake because you know the password. And if you succeed, now the client's going to send all of its messages using that PTK that you and the client share to you instead of the real access point. And so you can now see all the messages that the client wants to send. That makes you a man in the middle. That's the rogue access point attack. Okay, there's another one. So another attack is, well, Wi-Fi passwords might be kind of weak. So just like how we talked about in real life, a lot of people use weak passwords. Well, Wi-Fi passwords could also be weak. And so we could try and do a brute force attack. So here I'm crucially adding the word offline, because there are kind of 2 forms of brute force attacks. And we saw this when we talked about passwords. So there is one really silly attack that we're not even going to talk about because it's so silly. It's the online brute force attack. So what would that look like? Well, that would look like me clicking on the network on my computer, typing in the password, running the entire handshake, and it's not going to work because the password provided was wrong. And then what do? I try again. I type another password and hope that it works. And I type another password and hope that it works. So that's the online brute force attack, because I'm relying on the access point to tell me whether or not I got the password right. And just like we saw in the passwords lecture, this is going to be very futile, because the access point is going to get very sick of you after a couple of requests and say, okay, chill out. You're obviously just guessing. I'm going to not let you connect anymore. And I'm going to reject future authentication requests from you. So the online brute force attack, it's not even on the slides because it's so silly, and the access point can stop you with some rate limiting. So that's not what we're talking about. It's easy to get this confused and think that the brute force attack simply means I go onto the network and just start mashing passwords and hope that one of them works. That's not what we're doing, because the online brute force attack is kind of too easily stopped to even talk about. So instead, we're going to talk about the offline brute force attack, and this one is much more powerful because instead of waiting for the access point to tell me if I got it right or return an error to me, I'm going to record some information and then do all of the brute forcing myself. It's offline. I don't have to wait for the access point to tell me whether or not my guess is correct. I'm going to record some information and use the information to check my guesses myself. And if I check all the guesses myself, I'm not limited by the access point getting sick of me. I can check as many guesses as I want. So how does that work? So if I think about what an attacker can observe if they're looking at the network and watching somebody else connect, so maybe the attacker, they don't know the password. That's the setting of this attack. But maybe they watch someone else who does know the password run this handshake. So they're going to like peek in, watch someone else run it, and be like, oh man, I really wish I could be that client who knows the password, but I'm not. So I'm going to have to write down instead all the things that that client looked at. So what did that client send over the network that the attacker now knows? The client sent the authentication request. There's no cryptographic information there, but that's okay. But the client of the access point also sent nonces. So the attacker can write those down. Now the attacker knows a certain set of nonces. Do those help me learn the password? Not by themselves, but maybe with some other stuff they can. Also, crucially, the attacker can also write down these MICs, the message integrity codes from the cryptographic unit. The attacker can also write these down. And so the attacker knows the nonces, the attacker knows the MICs, and the attacker can write all of these values down. And now the attacker has a framework that they can use to try and guess if their guess is correct or check if their guess is correct without talking to the access point. So how will the attacker do this? The attacker will do this and check if their guess is correct by following the exact same derivation and seeing if the mix that the attacker generates match the mix that the client and the access point generate. So here's how it might go. The attacker knows exactly how the derivation protocol works. We assume the attacker knows the system. So the attacker is going to make a random guess. This Wi-Fi password, total guess. They're like, I don't know, maybe it's potato. Okay, so I take the Wi-Fi password guess potato. I derive a PSK. Is it correct? Probably not, but it's a guess. I take my guessed PSK. I combine it with the nonces. What licenses me to combine the PSK with the nonces? Like, why do I know these? Because they were sent over the network and I wrote them down. So I know them as the attacker. And the MAC addresses, we can assume the attacker knows the MAC addresses, because if I send messages back and forth, I can see the MAC addresses that are being like sent to and from, the to and from fields. Okay, so we assume all these things are known. I get a PTK out if I throw these into my hash soup. Is it correct? I don't know, it's a guess. It's probably not right, but it's my guess. And then using this PTK, what's the next step in the protocol? The next step is to use the PTK to generate these mix, think like HMAC. So if the attacker uses this PTK to generate the mix, well, if the PTK is correct, it's going to match the mix. And now the attacker knows that they found the correct password. If the PTK doesn't match, then the PTK used to generate the mix. And then if the mix do not match what the attacker wrote down, then the attacker knows, oh, I messed up. My initial guess must have been wrong. So I'm going to try this all over again. But crucially, none of this requires talking to the access point. All you have to do is write down this authentication request that you saw from somebody else, write down all these values, and that's going to give you the ability to check all of your guesses offline by yourself. You're no longer limited to the access point getting tired of you. You can try this as much as you want until you find something that works. And you are only limited by your own compute power and how secure the Wi-Fi password was in the first place. That's why it's the offline brute force attack, not an online attack. And that's why it's a lot more powerful, because here you don't have to rely on the access point to check your guesses for you and say like, nope, wrong password. Nope, wrong password again. Nope, wrong password. I'm getting tired of you. Instead, you can write down these values yourself. You can run these exact same derivations with a guess and then check if your guess is correct. I make a guess. I run all the same derivations. If I get the same MIC, then my guess must be correct. If I get a different MIC, then my guess must be incorrect. And that's what lets me check. Okay, it's the offline brute force attack. So that's attack 2 out of 3. Okay, the third one, it's not really an attack, but it is a property, which is, you might remember forward secrecy from the cryptography unit. If you don't remember it, we will talk about it again today, and then again in a couple of lectures, so it's okay if it doesn't sound super familiar. But forward secrecy is basically the property that if I write down a lot of stuff now, so suppose the attacker does not know the password now, but they write down all of this handshake and they also write down a bunch of encrypted messages. So they have these sitting here and they're just like, oh, if only there was a way to get the password, then I can decrypt all these messages. And so forward secrecy is the property that even if the attacker learns something in the future, they cannot take all this stuff that they've written down and decrypt messages. Unfortunately, WPA does not have this property because if an attacker writes down all this stuff and then later in time they learn the PSK, well, what can they do? Well, then they can take the PSK, they can use it to derive the PTK because they know the PSK, they wrote down the nonces, they can derive the PTK in purple, and now that they have the PTK, they can decrypt all the stuff that they wrote down in the past. So this does not provide forward secrecy because an attacker can write down a lot of stuff now, learn the password later, and still decrypt all the stuff that they wrote down in the past. In order for something to have forward secrecy, the attacker should not be able to do this. Okay. So that's the third kind of attack. It's not really an attack, but it's a property that we wish we had, but we don't in this case. The attacker can write down a bunch of values and then in the future, learn the password, use the password to derive the PTK in purple, and then use the PTK to decrypt all sorts of stuff that they wrote down in the past. Okay, so those are our three attacks. Rogue AP, where was this? Okay, Rogue AP, pretend to be the access point. You have to know the password, but if you know the password, pretend to be the access point. You can upgrade yourself to a man in the middle. Offline brute force attack. This one is useful if you do not know the password, but you can write down all these values. It gives you a tool that you can use to make a guess and check your guess without talking to the access point, so that you're only limited by your own compute power and you don't have to wait for the access point to get sick of you. Finally, there's no forward secrecy because an attacker can write down these values and the encrypted messages. And in the future, if someone ever tells them the password or they ever learn it, they can come back and take these values that they wrote down and decrypt them and figure out what you were saying in the past. So there's no forward secrecy. Okay, those are the three attacks of the day that you have to know. Anything else you would like to know about them? Okay, sounds good. So how do you stop them? You have to upgrade your WPA and use a more fancy version called WPA Enterprise. So this one's going to sound a little bit like too good to be true, and we're going to have to use some protocols from later lectures to really make this work. But here's how it's going to work. So the main problem is that think about yes, there were all these different handshakes, and I derived 20 different keys with different colors. But ultimately, what was the only piece of secrecy that separated users that are legitimate and attackers who are not legitimate? The only piece of secrecy from which all other secrecy was derived is the password. That's the only thing that's secret. Every other secret value, PSK, PTK, GTK, all of that came from knowing the password. So in other words, if you know the password, you've unlocked all this other stuff. That's the core issue, is that everyone has only one password that they all share. And if you know that password, you can derive everything else. That's why the offline brute force attack was so powerful, because if you know the password, you're all set. That's why the rogue AP attack, I guess, was powerful. That's why the no forward secrecy thing applied. If you know the password, then kind of your host. Okay, or you can decrypt things in the future. So the core issue is that there's only one secret value and everyone shares the same secret value. It's the one and only value. It's the Wi-Fi password. And so to fix this, we are instead going to give everyone a different password. So now it's no longer enough to just give your username, just to give the password that everyone shares. Instead, every one of us is going to have a different username and every one of us is going to have a different password. So if you think about EduRoam, which is the Wi-Fi network at Berkeley here, if you've ever logged into EduRoam before, they want a username and they want a password. So EduRoam uses WPA Enterprise. But if you think about a home Wi-Fi network or something, maybe you don't need a username. That would be a WPA2 or WPA PSK implementation. So the difference is that if you need to supply a username and everyone has a different password, you've upgraded to using WPA Enterprise. Okay, so how does this one work? Well, now the access point is going to be some sort of authentication server. And so the way that it's going to work is, again, most of this is going to come into clear view when we talk about TLS in a couple of lectures, but somehow we're going to use some cryptography magic to form a secure connection to the authentication server. And this is going to allow us to know that it's the real authentication server, not an impersonator, not a rogue AP. And it's also going to confirm that our communications are secure. How can this magic cryptography possibly work? You'll have to come back in 2 weeks to find out. But somehow, we're going to form a secure channel to the authentication server, and we're going to enter our username and password to the authentication server. The server is going to check if our username and password is correct. And if they're correct, the authentication server is going to send us a one-time key to replace the PSK. So most of WPA Enterprise actually works exactly the same. There's still a PTK that everyone generates. There's still a group key that everyone uses. The only step that gets swapped out is that very first step where we generated blue PSK. So in the older model, the way that we generated blue was we just took the password, hashed it, got the PSK. In this newer model, the way that you get the PSK is you walk up to a secure authentication server, present your username and password. If they're correct, you get a one-time PSK to use, and that PSK is unique to you. It's different for every single communication. It's one-time use only, and it's a lot more secure than the password because it's high entropy. Okay, so that's the fix that we're going to make, and it's going to solve those 3 attacks that we talked about. There are still other attacks that are possible that we're not going to talk about here, but the 3 attacks that got stopped are the rogue AP attack got stopped. Why is that? Because now the authentication server is going to somehow be authenticated. There's no way to impersonate them. TLS will provide that to us in a couple of lectures. The brute force attack is going to be a lot harder, basically impossible at this point, because the secret value, the blue PSK that you're using, is no longer derived from a password that's insecure. It is randomly generated, and the odds of guessing like a 256-bit random string, like 0, right? Astronomically unlikely. And finally, this also solves the forward secrecy problem because that PSK is used once and then thrown away. So if someone records a bunch of messages, they're still not going to be able to learn the PSK in the future. It's a one-time key. As soon as you're done using it, you throw it away. So that's what gives us forward secrecy. So WP Enterprise is nice. It stops these 3 attacks. In general, it doesn't always stop all of the attacks. There are still like higher layer attacks that are problems. But for the context, or for the story that we're building here, it stops the attacks that we discussed. Okay. Final note here, because people ask it every semester. People ask, why is WPA layer 1? Okay, it's weird. I know it's weird, but a lot of the protocols that we're talking about, remember, they don't fit cleanly into the model. So that model that I showed you with like layer 1, 2, 3, 4, 7, like it's kind of an outdated model. And in real life, a lot of protocols don't cleanly fit into one of the layers. WPA is one of those cases. So sometimes people argue that it's layer 1 because it involves like the wireless messages being sent back and forth. Sometimes people argue that it's layer 2 because it's happening at a link or a local network layer. So is there a really good answer? Not really. Would we ever quiz you and say like, please tell me what layer it's at? No, because people in general don't agree on the answer. So don't worry too much about what layer WPA sits at. The main things that matter are how we built that protocol to help secure messages and make sure that everyone with the password has a key, everyone without the password cannot get the key, and also how those attacks work. So the protocol itself is what matters. What layer it lives in, we don't really care because those layers are a little bit outdated. Okay. So anything else you want to know about ARP, DHCP, WPA? Otherwise, I'll summarize and then I'll like slightly talk about next time stuff and then we can go home. Okay. So quick summary, we talked about the classes of attackers from last time. They're going to come up over and over again, so make sure that you get super familiar with the 3 classes of attackers. We talked about ARP and DHCP, which are kind of cousins in the sense that they both have the same vulnerabilities. I broadcast the question to the world, and I accept the first answer that comes back. In both cases, there's no way to trust the answer that comes back. In both cases, there's a race condition in which the first answer that comes back, even if it's malicious, gets accepted. And in both cases, it's kind of hard to defend against because these protocols are simply too simple to, I said simply too simple. Okay, they're too simple to stop those attacks. So we're going to have to wait for higher layers to help us. Okay, and then finally, we talked about WPA for Wi-Fi connections. And again, what layer it lives at, I don't really care. The important thing is that we had this handshake, and the key parts of the handshake were that, where's my handshake? The key parts of the handshake were that, okay, there's my handshake. key parts of the handshake were that both sides started with a password, they derived the PSK and then they derived the PTK, all happening offline. They do not exchange this key over the channel so that other people can't see it. There is a nonce, which helps us make sure that the keys derived are different for every single person. There's a group key, which we use to broadcast messages to everyone else. And then we talked about the 3 attacks and how WPA Enterprise stops them. Okay. Final thoughts on any of this low-level stuff? WPA, ARP, DHCP types of attackers. That one project 2 thing that I showed you at the beginning. Anything else? Okay. So in the interest of staying ahead, this happens like every other semester, I'd say. I will show you one more thing about the IP layer. So we'll move up from layers 1 and 2 into layer 3, and then we'll be done. And we'll save layer 4 and beyond for next time. Okay. So layer 3, I'm just going to give you a quick whirlwind speed tour. If you want more information on this, I guess go take 188 or 168. If it's full, go on their website and check or something. I don't know. I can help you with that. But let's talk briefly about what happens at layer 3. Okay. So remember, at layer 3, this is where we're going to take all those little local networks, and you can think of them as like little apartment complexes, and we're going to use a big network of routers and like post offices to link them all up and connect the whole world. Okay. And so at layer 3, the protocol that lives at layer 3 is called the Internet Protocol, or IP. This is the protocol that everyone uses to talk over the internet. So later we'll see some layers like layer 4, there's a choice of protocols, but at layer 3, there's no choice. Everyone uses this to connect up all those little local networks together. So everyone uses the IP protocol or the internet protocol. As we've already seen, everyone has a unique IP address, right? Technically not unique, but for the purposes of this class, unique is good enough. We talked about how IP addresses have evolved over the years. So over the years, I think is fair. So back in the day, IP addresses were 32-bit values, and the way that you wrote them was you just wrote 4 numbers with dots between them. That's like classic IP. But then eventually they ran out of these, so they started to issue IPv6 addresses. These are longer, they're 128 bits, so we're never running out of these, but these are longer, and to write them you use hex and colons. Why? I don't know. People have interesting ways of writing things. Okay, you don't have to memorize how to write these. The important thing is if you see one of these, you should know that it's like an IPv6 address. Okay, we talked about how they're not really unique. There's something called network address translation that we're not going to talk about that makes them not technically unique, but for the purposes of this class, it's good enough to assume they're unique. Okay. And again, the IP address itself contains information about where the computer is. So we're not going to talk about exactly how you read these numbers, but you can imagine somewhere in there, there's some information that tells the routers where this thing goes. So it's just like a real address. Like if I write a real address, like, I don't know, 123 Main Street, Berkeley, California, 94720, that address contains information about where I am in the world. And so it allows people sending messages to know where to forward that packet. IP addresses have the same property, even if we're not going to talk about the specific numbers and what they mean. Okay. So one more thing you should remember from layer 3 is that because of the way that computers are wired up in that like network of network structure, it's not always going to be the case that a computer is directly connected to every other computer in the world. That doesn't scale. It's not how we build the internet. So if I want to send something to my friend in like Australia, which is a country I've chosen totally at random, and we choose a different one every semester. Okay, so if I want to send a message to my friend in Australia, I cannot send a message directly to my friend, but I can send a message over layer 3. And what the layer 3 protocols are going to do is it's going to send a message from me to some other router. That router is going to say, well, I can't reach Australia, but I'm going to send it this way because it's going to get you closer. So that router will send it forward to another router, and then that router is going to send it forward to another router. So it can take many, many hops across the world for my message to reach its ultimate destination. In the same way that if I was sending mail, there's no like dedicated mailman who's going to like swim across the ocean and take my message to Australia. Instead, the mailman's probably going to have to take this message and route it across a bunch of different post offices to get the message to its final destination. Okay, great. So one extra vocabulary term for you is that sometimes people will say that IPs belong to subnets, which is just a fancy way of saying there are a group of addresses. They all start with the same sets of numbers, the same sets of bits, and these addresses are somehow like in the same geographic region or like close to each other. So somehow, again, these numbers, they tell me something about where the addresses are. Like I don't have enough expertise to tell you how that's true, but somehow these addresses, they can be grouped into subnets, and the subnets can help me figure out exactly where the messages should go. It's like if I had an address and the address said like Australia, well, maybe you don't know exactly where the message should go, but okay, Australia, like that way, and you can send the message in the right direction. Okay. Great, here's some more words. So how do I send a packet in a local network? I can still use IP to do it. So IP is the layer 3 protocol. It allows you to send things to everyone in the world. That could be people in other continents. It could also be your neighbor. So how do you send a message to someone nearby you in the same local network at IP? You can still use IP, right? You take the message at the highest layer, you wrap all those headers around, including the IP layer. And so what would happen here is that you would check the destination IP, and you realize using the information in the number, like, wait a minute, this person is like my neighbor. This is not someone in Australia. This person is in the same local network as me, so I don't have to go through any ridiculous like router hops to get this message to its destination. And so the IP protocol will look at the subnet, look at the IP address, and realize, you know what? This does not need any ridiculous router hops to get to its destination. I'm just going to use ARP to figure out what the MAC address is, and then use my layer 2 protocols to send this only using a single hop to its destination, and I'm done. So IP can also be used to send messages within the local network. The protocol would look at the IP address, realize it's close by, use ARP to figure out the MAC address, and send it over a single hop to its destination, and you're done. By contrast, if you want to send a message to someone who's far away, not in the same local network, then instead of just sending it across a single hop to its final destination, you send the packet to the gateway or the router, and then the gateway now has its job to send it somewhere else that's closer, and then maybe that gateway sends it somewhere else that's closer. And so this packet could take multiple hops to reach its destination. Okay. Here's another word that people use at the IP layer. Again, I don't know why people like using so many different terms at different layers, but they do, so we just have to live with it. So sometimes people call the local network an autonomous system. Why? It beats me, but that's what people call it. Another way you can think of an autonomous system is it's a bunch of computers that are like connected up together, and they're somehow operated by the same entity. And what does operated by the same entity mean? You can imagine that's something that relies on the real world. So maybe it's like, oh, these all belong to the same company, or they belong to the same university. So that's what the autonomous system is. You don't really have to know anything more beyond the fact that it's a fancy name for local networks. And so the protocol that actually figures out where the packet should get sent is called BGP. Again, you don't have to know what it stands for, and we're only going to scratch the surface of BGP. But this protocol is somehow going to have all the information and all the rules that say, I have a packet. It's going to this IP address. Where should it go? Should it go that way? Should it go that way? Which next router should I send it to? BGP is going to tell me how to do that. Here's a simplified picture. Okay. As we saw, there are lots of different autonomous systems, which is a fancy way of saying it's a local network with a router sitting inside. They're all connected together in some way. Some systems are connected directly, some are not. This is how the network looks in real life. Okay, so if this sender wants to send a message to the recipient, there is no direct connection. If I look at all these arrows, no direct arrow. So this message is going to have to send to the recipient over a couple of different hops through a couple of different autonomous systems. So how do these autonomous systems build this map? You can imagine that this map is not like sitting in front of me as a picture that I can look at to figure out where the messages should be sent. So the rough idea behind how these systems actually build this graph to figure out who they can reach and who they cannot reach is each system is going to announce to all of its neighbors who's reachable. So autonomous system 6 is going to announce to the world, I am connected to the recipient, I'm connected to autonomous system 5, I'm connected to autonomous system 4. Now all of its neighbors know that if I want to reach the recipient, I should go through 6. How do I know that? Because 6 just announced to the world and all of its neighbors that it can reach the recipient. So now 5 knows if I ever want to get to the recipient, I should send it to 6 because 6 claims to me that they can reach the recipient. Same thing with 4. If 4 wants to know, how do I get to the recipient? Well, I know that 6 said they can reach them, so I'll just send it to 6 and trust that they know what they're doing. Okay, so 4 and 5, they reasoned this out, they announced these to the world and all of its neighbors, and now 3 knows, okay, well, if I want to reach the recipient, I don't have a direct connection, but I think back to all the things I've heard, and I remember, oh, number 5 said that they can reach the recipient through 6 or whoever else. So if I ever want to go to the recipient, I'll just send it to 5 and let them take care of it. And so 3 realizes that 3 can reach the recipient by sending it to 5 and letting 5 take care of it the rest of the way. So 3 announces, I can reach the recipient through 5 and going the rest of the way. And 1 hears that and says, oh, you can get to the recipient? Okay, in that case, if I ever want to go to the recipient, I'll send it through 3 and let 3 take care of the rest. So when everyone announces their reachable destinations to all their neighbors, everyone can build up this kind of rough idea of where messages can be routed. In reality, the routing protocol is a lot more complicated. You can imagine there are lots of different routes through this network. Which one do you take? BGP answers all those questions in tons of gory detail, but it's not stuff that we're going to cover. So this is kind of as much as you have to know, but it is definitely a simplified picture, because in real life, there are lots of questions about which routes to take, which paths are shortest. BGP answers those, but we don't answer them in this class. Okay, so what are the attacks? Well, the main attack at this layer is it's spoofing, kind of like it always is, and so far at least. So the idea is that when you announce to the world who's reachable, I mean, you can lie, right? No one is going to check if you're right. So each autonomous system could lie and say, I can reach the recipient, even though I can't. And if you lie and say to the world that you can reach the recipient, even though you can't, well, now any messages meant for the recipient are going to come your way because you claim to be able to reach them. So if number 3 goes rogue and says, so if number 3 is like the attacker and it broadcasts and says, I can reach this person, well, maybe that's a lie. And if autonomous system number 3 is lying about being able to reach this person, well, now any messages meant for this person are going to come to number 3. And now number 3 gets to be a man in the middle and like modify those messages before sending them forward. So that's called BGP hijacking. You're hijacking the network by lying and claiming to be someone that, or claiming to be able to reach someone that you really cannot reach. And that's going to maybe convince other people to send packets your way. Okay, something else that can happen at this layer that we've already seen is spoofing. And spoofing is the idea that you can send a packet and lie about the source packet. So if you send an IP packet, you can lie and say, I can reach, or like, I am Alice when you're really Mallory. That's the idea behind spoofing. And in general, we assume that everyone can spoof. One of the defenses that can exist against spoofing happens at this layer. So in general, each autonomous system should be responsible for checking things like this. So for example, if you're a router and you see someone sending you a bunch of IP packets, but the IP packets have a bunch of different sender fields, like I'm Alice, and then the next packet, I'm Bob, and the next packet, I'm Evan, but well, then maybe the router is going to get suspicious and say like, oh, hold on, you're probably spoofing. I'm going to stop accepting these packets. So autonomous systems should, in theory, be able to check and stop source IPs from being set to the wrong value and stop you from lying. But in real life, some autonomous systems just do not, either because they were configured by the attacker, or they're under attacker control, or they're just not set up the right way. So like roughly speaking, some autonomous systems in the real world, they will stop spoofing by checking whether or not you're lying about who you are in the sender field, and some autonomous systems will not. And it really just depends on which system you're on and how you configured it. So those are the attacks at the IP layer. There's IP spoofing, which we've talked about already. Some systems defend against it, some don't. There's BGP hijacking, where the entire autonomous system is malicious and lies about who it can reach. And in both cases, I'm going to like, again, quote at you the same thing we've been quoting all day, which is that at this level, there's just not enough information or not enough cryptography to defend against these things. So instead, we're just going to accept them as a fact of life. And we're going to accept that, okay, at layers 1, 2, 3, man in the middle, they might just exist. There are simply ways for people to become man in the middle attackers, and there's nothing we can do about it. You're going to have to wait until next week when we're going to like destroy all the man in the middle attackers with a single protocol. So at this point, we're going to accept man in the middle attackers as a fact of life. And then like a week from now, you'll come back and then we'll like destroy all the man in the middle attackers together. Okay. So you can start backing up if you want. I'll like quickly tell you a summary of the last 10 minutes as you like walk out. So we talked about BGP. All you really have to know at this layer is that the internet is a network of networks. Each small network, each local network can be called an autonomous system. And the way that they connect up together is that everyone broadcasts the ways that they can reach other people in the network. And so if you lie and you broadcast that you're able to reach someone that you're not able to reach, that could convince other people to send you messages, could make you a man in the middle. Okay, that's it. So I will see you next time and we'll talk about layer 4 stuff. So we're moving up the stack. Okay.